Okay, so we're going to start this chapter, which deals with the topic of chemical kinetics. So, when we're talking about kinetics, it's important that we make a distinction between kinetics and thermodynamics. Thermodynamics basically deals with, does a reaction takes place? In other words, can we predict whether or not a reaction will take place? And we're going to talk about that in a later chapter. Kinetics, on the other hand, deals with how fast a reaction proceeds. So basically, we are concerned with speeds of reaction and the factors that affect the speed of a reaction. So the measurement of a reaction speed is the reaction rate, which by definition is the change in concentration of a reactant or product with time. And you'll notice here that you're given the units of reaction rate in m per second, but actually it can also be m per minutes, m per hours, m per microsecond. It all depends on how fast the reaction proceeds. Some reaction proceeds very quickly, goes to completion in a millisecond. There are other reactions that literally take centuries to go to completion, basically. So, the units are flexible to reflect the variety of speeds of different reactions. So if we take a hypothetical reaction A reacting to form B, right, we can express the rate in terms of the disappearance of A, and this is the way we express it. Rate is equal to minus delta A divided by delta T. Right now, in your previous math experience, you should be familiar, or if you're not, I'll just tell you now, whenever you see the symbol delta in this context, delta basically means change, right? So delta A means change in concentration of A over the time period represented by delta T, which is a change in time, right? Now, another way of expressing the rate of this reaction is in terms of the rate of the formation of the product. Rate is equal to delta B divided by delta T, right? And one thing I want to point out here is that obviously when a reaction is taking place, the products are being used up. I'm sorry, the reactants are being used up and the products are being formed. That is a reason why there is a negative sign here, because when the reaction is taking place, the change in concentration of the reactant is negative, right? So for that reason, we have a negative sign here in this expression where rate is equal to minus delta A over delta T. So that's very important for you to realize. In the case of the product, it's being formed, so its change is positive, so therefore there's no need for a sign here because we understand that this is positive. Okay, so this is just a pictorial representation of the same reaction. In this particular model, A will be represented by the black spheres. So the black spheres represents the molecules of A, and the red spheres represent the molecules of B. And as you can see, as time progresses, there is a conversion of the A molecules to the B molecules. So as you can see, as you go from one box to the other, the amount of A molecules decrease and the amount of the amount of B molecules increase, all right? And we can actually represent this as a graphical plot. So in this graph here, we have the number of molecules on the y-axis, the time on the x-axis, and as you can see here, the amount of molecules of B increases because, of course, it's being produced, while the amount of molecules of A decreases because, of course, it's being used up as the reaction progresses, all right? So again, the rate of the reaction would be equal to minus delta A over delta T, and the rate of the reaction with respect to B is given by this expression, all right? Okay, and for a real example, a real chemistry-related example, we can see here this reaction, the reaction between bromine and formic acid, that's what this is, to form bromide, hydrogen ions, and carbon dioxide. Now, bromine has an intense, of course, depending on the concentration, red color. And you'll notice as the reaction progresses, what happens, right? You see that the intensity of the color of bromine decreases until it disappears. The other substances have no color, so they won't interfere in terms of the appearance of the solution with respect to color. So the color here is only due to the bromine. So basically what this is indicating is that as time progresses, the concentration of bromine decreases, all right? Now, in this particular reaction, in order for us to measure the concentration, we monitor the concentration by basically monitoring the intensity of the color, right? Because the color intensity is directly proportional to the concentration. So there's an instrument that is known as a UV ultraviolet detector. Actually, it's an ultraviolet spectral photometer, which is used to detect um, light of a particular radiation in this case, or light of a particular wavelength. In this case, the light has a wavelength of 393 nanometers. So the way we use this instrument is that we set it such that it only detects that wavelength of light um, for bromine, because bromine absorbs specifically that wavelength of light. And as the reaction progresses, we basically plot or record the absorption, which is what the instrument measures, right? We record the absorption, which is, of course, proportional to the concentration of bromine. So therefore, by monitoring the absorption, we have an idea as to what the concentration of bromine is, and we can therefore see quantitatively how the absorption changes with time as the reaction progresses. All right. So that's a real example of monitoring how fast the reaction progresses. So we can actually collect data, because once we know what the absorption is, and we know that the absorption is proportional to the concentration of bromine, then we can basically do a record of the concentration of bromine and the um, corresponding time intervals, right? So at 0, the concentration was 0.0120, and then at 50 seconds, it decreases to 0.0101, and so on and so forth. And therefore, we can plot a graph, right? We can plot a graph of concentration of bromine on the y-axis versus time in seconds on the x-axis. And as you can see, you get a smooth curve here, all right? And we can, therefore, based on this plot, calculate the rate. Now, there are two types of rates of reaction that you need to be aware of, right? There's one type that is known as the average rate of reaction. And the average rate is what we talked about before. Specifically, as it relates to this reaction, we can express it as minus the change in concentration of bromine with the change in time, right? So basically, you have to take two time intervals over which you're going to calculate the average rate, all right? So another way of expressing it is the concentration final of bromine minus the initial bromine concentration divided by the time, the final time minus the initial time. So basically, this is used to calculate the average rate over a period of time for a reaction. And then you have what is known as the instantaneous rate, which is the rate at a specific instance in time. Now, in this particular case, you would have to actually have a plot of the graph in order to calculate the instantaneous rate at a particular time. And that is what is being demonstrated in the graph here. So if you want to calculate the instantaneous rate at, let's say, 100 seconds, right? So you draw a line from the 100 mark here on the x-axis to where it cuts the graph, and then you draw a tangent, and then you determine the slope of that tangent, right? And you should know about determining the slope of a curve. If you're given a graph, it's rise over run, right? So basically, it would be the difference between these 2 points here in terms of what you measure here on the x-axis, and these 2 points here in terms of what you measure over the y-axis, right? And of course, it would be a negative slope because bromine is being used up, and therefore we call that the instantaneous rate. So those are two different ways of measuring the rate of reaction. The average rate and the instantaneous rate. The average rate, of course, is over a particular time frame, while the instantaneous rate is the rate at a particular instant. Okay, so in this particular case here, the instantaneous rate at 100 seconds is 2.96 times 10 to the minus 5 m over seconds. And then at, whoops, I'm sorry. And then at 200 seconds, the instantaneous rate falls to 2.09 times 10 to the minus 5 m per second. And then finally, at 300 seconds, the rate is measured at 1.48 times 10 to the minus 5 m per second. So as you can see here, the reaction rate falls off as the concentration of bromine increases, which is what you'd expect, right? The less bromine you have present at a particular time, the less would be the instantaneous rate of the reaction. Okay, here is dealing with the same reaction, but this time what we're doing here is ultimately getting a relationship between the time and the rate, right? So we're not plotting time versus concentration, which was what was in the previous graph. We're showing you now the change in time over plotted against the change in rate. In fact, more technically correct to say that it's a rate being plotted versus time, because the rate here is on the y-axis, the time is on the x-axis, all right? And you'll notice that in this particular reaction, you have a straight line, all right? So what this tells us is that the rate is directly proportional to the concentration of bromine, right? That is based on the data and the graph that we have obtained right here. Another way of expressing this is that the rate is equal to K times the concentration of bromine. And you're going to learn about rate laws. This is what a rate law or the rate law for this reaction is, right? And we can rearrange this to get K is equal to rate over the concentration of bromine. So K is, of course, the constant of proportionality in this reaction. And one can see that K is constant because when you divide the rate in each case by the concentration, you see that the values are very, very close, 3.50, 3.49, right? So basically, the values range from 3.52 to 3.49. So that's a very narrow range, and therefore that is pretty much telling us that K is constant for this particular reaction, all right? Okay, so that is called a rate constant, as I said before, which is equal to 3.50 times 10 to the minus 3. So I think that's the average of all the rate constants that were determined here. Or you can determine that from the slope of the graph that you get here, all right? Okay, another example of a reaction, the decomposition of hydrogen peroxide. And in this case here, it is more convenient for us to monitor this reaction in terms of the pressure of the oxygen that is formed. Now we know the ideal gas equation, PV is equal to nRT. We can rearrange that to get an expression relating the pressure of oxygen to the concentration of oxygen. Again, it's a linear relationship, so therefore monitoring the pressure is an effective way, a very good way of monitoring the concentration of oxygen. And in this particular case, the rate of the reaction would be measured by the change in the concentration of oxygen divided by the change in time, which works out to be equal to 1 over RT times the change in pressure over change in time. And when this reaction is done and the pressure measurements are taken over different time intervals, again, we end up with a smooth curve, and we can find out the instantaneous rate, just like we did in the previous example. We choose a point at which you want to calculate or determine the instantaneous rate, which I think is 400 minutes here. You draw your line, which is a tangent, and then determine the slope. And in this case, the slope is 0.12 millimeters mercury per minute. So that's basically the instantaneous rate of the reaction at that particular point in time. Okay, we're going to stop here because the next discussion we're going to talk about is the relationship between the reaction rates and stoichiometry. Okay, until next time.